In the last video, we looked at the trend for ionization energy going down a group on the periodic table. In this video, we're going to look at the general trend for going across a period. And so here we are in period 2. And the general trend as you move to the right across the period is for there to be an increase in the ionization energy. And once again, in this video, we're only talking about the first ionization energy. So if we look at lithium, right, lithium has an ionization energy of positive 520 kilojoules per mole. And then we go to beryllium, and that number increases. And you can see in general, the trend is to increase. So carbons increases from that, nitrogen's increases from that, and so you can see these numbers are getting bigger and bigger. So there are a couple exceptions to this general trend that we can see. We can see that from beryllium to boron, right, there's actually a drop in the ionization energy. And also from nitrogen to oxygen, there's a drop in the ionization energy. And so we will talk about those exceptions to the general trend. But first, let's analyze lithium and beryllium and see if we can figure out why, in general, as you move across a period, there's an increase in the ionization energy. And so let's look at these diagrams down here, and let's go ahead and draw in lithium and beryllium. So first, lithium with an atomic number of 3, so 3 protons in the nucleus, and the electron configuration for lithium is 1s2, 2s1. So 2 electrons in the first energy level and an s orbital. So those are the 2 electrons in the first energy level occupying an s orbital. And in the second energy level, right, 1 electron. So let's go ahead and put in that 1 electron there. For beryllium, atomic number of 4, so we have 4 protons in the nucleus. And so for beryllium, the electron configuration is 1s2, 2s2. And so in the first energy level, we have our 2 electrons. And in the second energy level, we also have 2 electrons, so a neutral atom of beryllium. So let's go ahead and put in those 2 electrons in the second energy level. And again, these diagrams are not perfect, but they're just going to help us try to understand the simple concepts for figuring out this trend here. And so let's analyze the ionization energy for these 2 atoms. And so let's use the same factors that we talked about in the last video. So the first factor was nuclear charge. Let's go ahead and write nuclear charge here. So the nuclear charge, of course, is referring to how many protons you have in your nucleus. And the more protons you have, the more an attractive force there will be for that outer electron. So if we look at lithium, right, with a charge of +3 in the nucleus, right, that's going to attract this outer electron. So there's a +3 charge. For beryllium, right, with a +4 charge, it's going to attract this electron right here. And since it's +4, right, you would think that it would have more of an attractive force for one of these outer electrons. So just thinking about nuclear charge, we would expect there to be a greater attractive force for one of the outer electrons in beryllium than lithium. So therefore, you would think that it would take more energy to pull that outer electron away. And so therefore, an increase in the ionization energy. So just thinking about nuclear charge, we would say there would need to be an increase in the ionization energy. Next, let's think about electron shielding or electron screening. So electron shielding or electron screening. So the idea is that inner shell electrons will screen the outer electron from the effect of the nucleus, right? So if we look at lithium, right, this electron right here is going to repel this outer electron, and this electron over here on the right is also going to repel this electron. So they shield that outer electron from the pull of the nucleus. They screen it from the positive charge. And if we look at beryllium, right, so once again, these inner shell electrons are going to do the exact same thing. They are going to shield this outer electron from the effects of the nucleus. And so we're going to have approximately the same amount of electron shielding here. Now for beryllium, beryllium does have an electron right here which could repel this electron, and that probably does contribute some to it. But in general, the inner shell electrons do more of the shielding or the screening than this electron, because this electron is also in the 2s orbital. So these inner shell electrons have more an effect on screening. So we're going to say that the screening or the shielding is approximately the same for these two atoms, and so therefore there's really no effect on the ionization energy. And then finally, distance, right? That was the third factor that we talked about. So distance, that outer electron is from the nucleus. Well, this electron in lithium, right, is in a 2s orbital, so on average it's a certain distance from the nucleus. And this electron that we're talking about in beryllium is also in a 2s orbital, so it's on average about the same distance from the nucleus. And so the distance has really not much of an effect at all, or no effect on the ionization energy. And so if distance has no effect and electron screening or electron shielding has no effect, really all we have to think about is the nuclear charge here. And let's go ahead and calculate the effective nuclear charge for both of these atoms really quickly. So for lithium, right, the effective nuclear charge would be the number of protons, so that's +3. So we're calculating effective nuclear charge for lithium, so it'd be +3, minus the number of shielding electrons, so that would be this one and this one, so +3 minus 2, so we get an effective nuclear charge of close to +1. In reality, it's about 1.3 when you do the more complicated calculation. For beryllium, right, the effective nuclear charge would be the number of protons, which would have increased, right, to +4. And the shielding electrons, once again, we're only going to consider these inner shell electrons for our very simplified calculation of effective nuclear charge. And so we would get an effective nuclear charge of close to +2. In reality, it's approximately 1.9 when you do the more complicated calculation. And so we can see that we have an increased effective nuclear charge, right, from +1 to +2. So as you move across a period, you're going to have an increase in the effective nuclear charge. And that's the reason that's given for the trend of an increase in ionization energy as you move across the period on the periodic table. So let's next talk about exceptions to that. And so the next one we see is right, we went from 520 for lithium to an increase for beryllium because of the increased nuclear charge. And then when we go from beryllium to boron, we see this drop, right? We go from 900 to 800. So that's not following our general trend. Let's see if we can explain it though. So let's draw a picture for boron over here. So boron has one more proton in the nucleus. So there's 5 protons in the nucleus, so +5. In a neutral atom of boron, there'd be 5 electrons. So let's go ahead and write the electron configuration for boron. It would be 1s2, 2s2, and then we would go to p1. So for boron, we go ahead and show the 2 electrons in the s orbital, in the 1s orbital, the 2 electrons in the 2s orbital, and then this 1 electron in the p orbital, right, on average, an electron in a p orbital is a little bit further away from the nucleus. So I'm going to represent this electron right here. Right, so that would be the outermost electron on, so this p electron right here. So that's the one that's going to be taken away in terms of ionization. And so let's once again think about our 3 factors, right? So first, nuclear charge, right? Well, compared to beryllium, right, that had a +4 charge in the nucleus, boron has a +5 charge in the nucleus, so we have an increased nuclear charge, so we could think about this electron, right, as experiencing a greater attraction for the nucleus. And so just thinking about nuclear charge, we might think, oh, there's an increase in the ionization energy to follow our general trend. But we have these other 2 factors to think about too. So if we think about electron shielding, right, so we know this outer electron, this electron in the 2p orbital, is shielded by these inner electrons in the 1s, right? So there's definitely some shielding due to those electrons in the 1s orbital, like that. But since on average this electron in the p orbital is a little bit further away than these electrons here, right? So these electrons here are in the 2s orbital, right? So they're all in the second energy level, but on average the electrons in the s orbital are a little bit closer to the nucleus. And so there's a little bit of shielding that's going to go on here. And so there's a little bit of extra shielding for that electron in the p orbital. And so because of that extra shielding or screening, it's not going to feel as much of a pull from the nucleus from that increased nuclear charge. And so just thinking about electron shielding, right, that's screening that outer electron from the positive attraction, from the attraction of the nucleus, and therefore should be easier to take that electron away. So shielding says a decrease in ionization energy. Finally, distance. Right, so for thinking about distance, right, this, again, on average, this outer electron here is a little bit further away from the nucleus, right, than this electron over here in beryllium. And so that since it's further away, right, there's less of an attractive force for the nucleus, and so therefore it takes a little bit less energy to pull that electron away. And so because just thinking about distance, we could say there's a decrease in the ionization energy. And so we add up all three of these factors, right? So when we think about distance says decrease in ionization energy, electron shielding says decrease in ionization energy. Those two turn out to be a little bit more important than this increased ionization energy due to the increased nuclear charge. And so that's the reason for this drop in ionization energy that you see from beryllium to boron. So that explains this first exception to the general trend. Next, let's talk about this other exception here. So this drop in ionization energy that would be from nitrogen to oxygen. And so let's go ahead and write the electron configurations for nitrogen and oxygen. So first let's write the electron configuration for nitrogen. Well, that would be 1s2, 2s2, and then 2p3. So let's go ahead and do that in orbital notation. So we have the 1s orbital, the 2s orbital, and then our p orbitals like that. And so let's go ahead and put in these electrons in blue, I guess. So 1s2 would now take care of the first energy level, right? And then second energy level, 2 electrons, so that takes care of those electrons right here. And then the p orbital, we have 1, 2, and 3. For oxygen, right, next let's go ahead and write the electron configuration for oxygen. One more electron to think about, so 1s2, 2s2, and then 2p4. So when we write our orbital notation, right, we go ahead and fill in those electrons. I'll use blue again here. So if we think about those electrons, so 1s2, that takes care of these, and then 2s2. And then we have 2p4, so we go 1, 2, 3, and then that fourth electron, right, that's going to pair up spins. That's going to go into this orbital right here. And because that electron in magenta, right, is repelled by that electron in blue, that means that it's a little bit easier to remove that electron. So a little bit of electron-electron repulsion there means it's easier to remove the electron, therefore it takes less energy to remove that last electron than it would to remove an electron from over here for nitrogen. And so that's the reason that you usually see given for this decrease in the ionization energy from nitrogen to oxygen. So we've talked about the two exceptions, but once again, in general, right, as you move across a period in the periodic table, you're going to get an increase in the ionization energy, and that's due to the increased number of protons in the nucleus pulling the outer electron, having a greater attractive force for that outer electron, and therefore making it harder to pull that electron away, resulting in an increase in ionization energy.